Hello everybody. This is the first of two videos designed to introduce you to the betweenness centrality for nodes in a network. In this first video, we're going to motivate this centrality metric, and we're also going to lay the groundwork for later computing betweenness centrality for the nodes in our network. In our second video, we're going to go into the specifics of how to compute the betweenness centrality metric for each node in the network. Let's get started. First, remember there are two different types of metrics. The first type is an attempt to summarize something about the entire network. Metrics like order, size, density, diameter, all of these things try to describe the network as a whole. In addition to this, we also consider centralities, which are metrics that describe individual nodes inside your network and how they relate to the other nodes. The first example that you've probably seen of this is degree centrality, where for each node we keep track of how many edges actually touch that node. Today, we have another centrality, which is betweenness centrality. So keep in mind that when we're talking about betweenness centrality, there's going to be a unique measurement for each node inside of our network. I want to start with a little bit of motivation. Let's consider this example. Suppose we're in a classroom where there are 9 students. We have 4 students who are doing a very good job of paying attention and doing their work, but we have a small network of 5 students who are all passing notes to one another. There are many different ways to think about betweenness centrality. One very common way, and one you've probably seen if you've read Wikipedia or some other sources, is to think about, for the node of interest, what would happen to the connectivity of the network if we were to remove it. So for example, if we were to remove this node here, or this student, how would that affect the ability to pass notes between the remaining students? I want to take a slightly different approach. I think it'll be a little bit more fun. Given this network of students passing notes, let's ask the question, who's most likely to get caught inside of the classroom? There are a couple of things to consider. First of all, if you're a network of students passing notes, the whole point of this will be to pass notes as quickly as possible. You're not going to take a note passing path that's meandering. You won't go first from this student to this student, then across, then over, then over. The students will naturally want to use shortest paths when getting their messages through the network. Another thing to realize is that certain students are naturally going to be at a higher risk than others. Take, for example, this student in the upper left-hand corner. This student, when passing notes, only has to worry about the notes that are either addressed to him or that he's sending to somebody else. However, if we consider this student here, right in the middle of our network, this student not only has to field her own notes to other people, but she's also going to have to pass along notes from other students in the class. So when it comes to just sheer volume of notes being passed, this student's going to be passing more notes than the one in the upper left. This student's going to be at a higher risk. So what we realize is that students that are between in the sense of the network, what you might call between students, end up passing more notes than other students. They're at a higher risk of being caught inside of this network. So our purpose moving forward is to try to define a metric that captures this notion of betweenness, or captures the risk of the students in this note-passing network of being caught. This is what we're going to eventually call betweenness centrality. In our first step, we're going to take this basic picture here, we're going to sterilize it a little bit and make it look a little more mathematical. So we have that same basic network structure. We've replaced students with just letters A, B, C, D, and E. And now our first step is we're going to start by listing all possible pairs of nodes. Notice that we had to do this when we were computing things like diameter because we wanted to consider the shortest paths that are inside of our network. So we'll do it again. As a quick review, if you want to list all possible pairs of nodes, you can follow this type of process. The first thing, we can kind of ignore the connections because we're just looking at possible pairings of nodes. Start with any node. I think A is probably a logical place to start. And consider what other nodes can you pair with A. We could do AB, we could do AC, we could do AD, and AE. This sort of exhausts all pairings with A. So what we're going to do is cross out A and start over with a new node left over in the network. Say B. We can pair B with C, B with D, B with E. We would cross that node out. And now we will continue with this process until eventually we run out of possible pairings of nodes. So if you want to do the rest of the list, pause the video and do this just for practice. but we're going to move on. Once we have our list of all possible pairs of nodes, our next task is going to be to list out the shortest paths that exist between a given pair of nodes. In addition to this, as we go through, we're going to keep track of the total count, the total number of shortest paths that exist between two nodes. So let's get started. We'll start by considering AB. We'll notice that there's only one shortest path, and it's the direct line from A to B. The same is true of A and C, as well as A and D. But when we want to pass a note from student A to student E, we have to filter through student B. So this is the first case where we have a shortest path which isn't a direct line. Even in this case, however, there is only one shortest path to consider. When we look at B to C, we could filter through student A, or we could just as well filter through student D. So in this case, we have two shortest paths, and we're going to list them both inside of our table. In more general cases, we would list all of the possible shortest paths in between the two nodes. If you want to pause the video at this point and fill out the rest of the table, I recommend you do so. You can compare your answers to the ones on the next slide. Here is our completed table. Notice that we have a list of every possible pairing of nodes. For each pairing of nodes, we list out each possible shortest path between them. And then in our final column, we keep track of the total number of shortest paths between that pair of nodes. Compare this with the answers that you have. In our next step, what we want to do is start reducing down this table so that it only focuses on between nodes. This is our primary interest for betweenness centrality. Between nodes are going to be nodes that appear in the middle, not at the start or end, but in the middle of a shortest path. So we're going to take our table, we're going to consider the shortest paths column, and we're going to start kind of erasing any node that's at the beginning or the end of one of the shortest paths. In a sense, all we have to do here is ignore the starting and ending nodes for that column. To that end, we see that we can get rid of both A and B in our first shortest path. The same is true of A and C and A and D. And it's only when we consider the row associated to this pairing, nodes A and E, that we finally observe our first between node. Notice that B appears in the middle of the shortest path between A and E. And we're not going to cross it out because it doesn't appear at the start or the finish. This is a between node. At this point, if you want to pause the video and cross out all the other starting and ending nodes for the shortest paths that appear in this column, I recommend you do that, and then you can check your answer. So here's our answer. We have looked over all of our shortest paths, and we've erased any starting or finishing node, leaving only the between nodes left in the shortest paths column. With this table, we can see that we can start to ignore entire rows of the full table. For example, all of these rows don't have any between nodes present. If we get rid of those nodes, we're left with what we'll call a reduced table. In the reduced table, the nodes that appear in the middle of a shortest path are going to be all of our between nodes, and we're going to use this to eventually compute betweenness centrality. So here's what we've identified with this reduced table. All of the nodes that still appear inside the shortest paths, they haven't been erased. These are nodes that appear in the middle of a shortest path between two other nodes. We're going to refer to these as between nodes. So you'll notice if we look at what's left over, we have A, we have B, and we have D. Now they may appear multiple times, but we'll deal with that in another video. Notice that there are some nodes in our network which don't appear anymore in the reduced table shortest paths column. Specifically, C and E don't appear after we've reduced our table. This equates to essentially the fact that C and E will never appear in the middle of a shortest path between two other nodes in the network. For the purposes of this first video, here's the main distinction we want to make. We can split, after computing a reduced table, we can split our nodes into two groups, the between nodes and the nodes that are not still remaining in the reduced table, the shortest paths. We highlight them as such. The basic idea, the real reason these are different, is because the betweenness centrality of the nodes not in the reduced table is going to be set to 0. The betweenness centrality of the nodes that are in the reduced table, the between nodes, these will be non-zero, and in the next video we're going to learn how to compute these. Here's a rough interpretation of what's going on. Remember our example of a network of students passing notes in class. We were trying to figure out which student's most likely to get caught. A student like that of node C only has to deal with his own notes. If student C gets a note, it's because it's his note. Somebody wants to send information to him. If student C passes a note, it's because he is sending information to somebody else. For that reason, student C is probably at the lowest risk of being caught, since he only has to deal with his own notes. For that reason, we set his betweenness centrality to be the smallest, 0. For the other nodes in the graph, for example, student B, they don't have the luxury of only having to field their own notes. They also act as a go-between between two other students. For example, student B has to also pass notes that A wants to get to E. So with this increased risk, we get a non-zero betweenness centrality. This does leave us with one question. How can we express this risk comparatively between those nodes that are also between nodes? Is B at a higher risk than A? Is B at a higher risk than D? How can we express the betweenness of these nodes with a comparable metric? This is going to be the content of our second video.